Okay, we're going to run through some kinematics now. So we've covered vectors and what they are. Now we're going to look at using vectors. And specifically the vectors that have to do with motion. Okay, so kinematics is essentially the mathematics of moving objects. So let's start with a little recall here. So this means remember. Remember from your past experiences that velocity is described as the change in position divided by the change of time, or it's the rate of change in displacement. Okay? And that acceleration is the rate of change of velocity. And we tend to think about this graphically, or we like to think about this graphically. So what that means is we were to build ourselves a position time graph, so position in meters, time in seconds, okay? We can track or plot motion using something like this. So we'll just pull a little number line up here so we can reference what we're talking about. Okay, so number line 0, 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. Okay, and we'll say that that's meters. Okay, and we're going to talk about motion with respect to this number line. Okay, so first things first. Motion always occurs over a span of time, right? You know, if you have no time span, you can't move anywhere. So it always happens over a time span. So this is tracking where we are in time, and this is tracking where we are in space, right? There's a way of looking at space in terms of time, I guess, okay? So one type of motion that we might have is we might just have someone moving at a constant velocity, say from left to right, all right? They might start here and move to here, and it might take them some amount of time. So if we start to the left and move to the right, we might get a graph that looks kind of like, let's get a color that's going to show up, that. Okay, so what we're talking about here is an object moving at a constant rate. Okay, in other words, its displacement changes is constant the whole time. All right, right at about this time, say this is 10 seconds, right at about 5 seconds, the object's at 0, and sometimes later they're at positive 4. Okay, so this should look familiar to you. All right, now if we take the slope of this graph, so we're just quickly reviewing here. If we take the slope of this graph, okay, what we're looking at is the rise over the run, right? But in this case, rise, the change in y, is really the displacement, right? It's the change in position or the displacement, okay? So delta d. And then the change in time, right, the run, the change in x is delta t. So we want to find the slope here. We're actually going to go delta d over delta t, and then we realize that that is the velocity of the object, okay? So step one, slope of your dt graph equals velocity of the object, okay? That's day one stuff in kinematics. The second thing we're going to now do is we're going to take a velocity time picture here. We're going to look at this in terms of velocity time. So again, this is review of stuff we did last year. We're just making sure everyone's on the same page with it. Okay. So if we have a velocity time graph and it's the slope, we'll draw a little arrow to just say that. The slope we get here gives us our points for this graph. Okay, so this graph down here is going to be our velocity in meters per second versus time. Well, this is kind of a boring scenario because really the velocity is the same the whole time. The slope never changes. Okay, so it's a positive slope of some value. Oops, let's do a straight line. Something like this, right? Your velocity is just constant the whole time and it's positive. So the motion of the object that we're talking about is something that just, you know, bops along at a very regular rate. It's always covering the same distance in the same amount of time, right? Some object is moving along the number line from position to position to position to position, okay, covering exactly equal distances with every time period. Would we consider this to be an accelerated motion or not? No, it's uniform motion. There's no acceleration. The velocity is always the same, okay? And we can see that from our graph. We don't believe it, right? The velocity is always the same. So I'm going to look at this in one other sense, and you know, it's going to be based on this concept. So if we take this formula and we rearrange it, okay, we could come up with that your displacement, your change in position, is going to be equal to whatever velocity you have times the time interval that you're traveling over, right? Or distance is equal to velocity times time. That should be like conceptually easy to understand. If you travel 300 kilometers per hour, 300 kilometers per hour. If you have 100 kilometers per hour for 3 hours, how far have you gone? Well, 3 times 300, 3 times 100 is 300. Words are hard, okay? So let's look at this graph now and see how this relates. So have a peek here. What you can see is here's V and here's T. What we're really describing is like a rectangle that's kind of under here, right? Velocity times time. Let's just make this more clear. Velocity, right, times time gives me the area of this graph. That looks like this. Okay, so if I say velocity times time, what I'm really talking about is the area under the velocity time graph, right? We're finding the area of this rectangle, okay? And that, you know, comes to us from our formula, and it allows us to work our way back to this graph. This graph is made by the slope of that graph. This graph is made by the area. I'm going to make a different color, actually. Back to this purple. Of this graph. Right? So going one way, you're going delta D over delta T to get this. And the other way, you're going V times T to get that. Okay? So that's the second point that we're going to write down. 2. Area under a VT graph is equal to my change in position or my displacement. Okay, so last but not least, from this information, all right, we can create an acceleration time graph. And I'm just going to do this for demonstration purposes, just to stick with our little formula we're doing here. There is no acceleration on this object, right? It's got a constant velocity. Right after, we'll do an accelerated motion, though, okay? But for now, what we're going to say, and we just want to, we're building up these different relationships, how these graphs relate to one another. If we do an acceleration graph for this object, okay, we'll see here are units meters per second squared, units seconds, this is meters per second, and this is meters. We're going to see a relationship building up here right away. Okay, the acceleration of this object is 0, right? There's no acceleration. Well, how do I know that? Because the slope of this graph gives me this graph, right? Acceleration, oops, come on now. Acceleration is found as the rate of change of velocity. Well, if there's no change in velocity, I got 0 accelerations. Value is just simply 0. So we can continue our little connection thing here, and we go, whoop, slope. Okay, this is the slope of that. Now, here's your next question. If this is slope and that was slope, how do we get back to a velocity graph? So this found me what my change in displacement was, right? It's v times t. This should tell me find what my change in velocity is. Well, my change in velocity is 0, right? So it's 0 times t. It should just be 0. But we'll see in a second that there's situations where it's not 0. So the area under here, which happens to be 0, equals delta V. Let's see if our formula bears that out. Rearrange this formula and you'll see, when I rearrange it, let's use the same color. Delta V, okay, delta V comes equal to your acceleration value times your change in time, all right? So we're just rearranging that formula. You can imagine if we did have an acceleration, okay, that would tell us what our change in velocity was, okay? But we're going to save that for next. This is a situation where acceleration is just simply 0. And now one more thing I want to talk about here. Let's look at units, right? We got meters and seconds here. We are finding the slope by dividing meters by seconds. So we end up in meters per second here in our units. And now we're taking meters per second and dividing them by seconds again. So we have meters per second when we get down here. And what does that really mean? When we do have a changing acceleration, what it means is we're changing our velocity by this many meters per second every second. So it might be 2. Say I'm increasing my velocity 2 meters per second each second. Well, 2 meters per second, you know, after 6 seconds, I'm now going 12 meters per second. That sort of a thing, okay? So meters per second squared is the same as saying meters per second. And sometimes people like to think about it in terms of 2 different units. So a way to look at this, well, actually, you know what? Let's just move on to one where we actually do have an acceleration. So let's pause for now and get back there when we do have an acceleration. So I just want to write a couple more points here, actually, just before we wrap this up. We'll say that slope of VT equals the acceleration, and for area under acceleration time equals delta V, change in V. Okay, so let's continue on here and let's look at scenarios now where we have actual accelerated motion. So we're going to start with laying this down on a number line. Okay, and then we'll fire out some evenly spaced little points here. And we'll talk about where the object is in space and time. And we're going to have an object now that is accelerating. So it's going to start with very low velocity, and it's going to move right. That velocity is going to increase. And we're going to say that these are dots that represent where the object is at evenly spaced time intervals. Okay? So every little time interval, we'll say these are 1 second apart, say, that object has moved farther than it did in the last 1 second time interval. Okay? So this is 1 second, that's 1 second, 1 second, 1 second, 1 second, and 1 second. Okay, so we would say in just regular words, the object is traveling right and it is speeding up. So I just want to talk about this whole concept of speeding up. To make something speed up, you got to push it. You got to apply a force to it, right? So we're going to address that. We know force is equal to mass times acceleration, right? And we know that a force is a push or a pull on an object. And we know that the more massive the object is, the lower the acceleration, or the higher the force it is, the higher the acceleration. And what we can say from this, really, is that acceleration is proportional to the force applied. So why am I telling you this? I'm telling you this because we're going to think about what's going on in terms of acceleration based on thinking of acceleration as being caused by a push or a pull. I push on something in that direction, okay, and it's like no one can see what I'm doing because I'm on the online here. If I push in this direction, then I'm going to have a force in this direction. So this is a scenario where the acceleration is to the right and the velocity is to the right. And I want you to think about accelerations in terms of pushing on objects. Okay? When I push on them, that's the direction they're accelerating in. Okay? So thinking of accelerations abstract, but accelerations can't happen without a push. So just think of accelerations in terms of the pushes that make them happen. This will help you understand what's going on. So if I'm moving right and speeding up, I've got to be pushing right, and therefore I have a rightward acceleration. All right. So now we're going to look here. Okay, so we're going to say that for the first little period in time, right here, our velocity was, say, 0 meters per second. Okay? Then, and we'll call this at time equals 0, right at the start. That's the velocity it has right at the beginning. It's not moving. Then by the time it gets here, its velocity is going to be 1 meter per second. Then our velocity here is 2 meters per second. Then here it's 3 meters per second. Here it's 4 meters per second. 1, 2, 3, well, almost. Here 5 meters per second. And here it's going 6 meters per second. Okay? So these are 1 second intervals. That's t equals 0, t equals 1, t equals 2, t equals 3, t equals 4, and t equals, say, 5. Okay? So 0. Oh, I missed 1. Oh, nuts. Oh, no, I have 1. 1's there. Okay, good. 1 is there. Awesome. And maybe we'll call this. So this is 0, 1 second, 2 seconds, 3 seconds, 4 seconds, and 5 seconds. Okay. All right. So let's look at this a little more closely. I want to look at what's happening to just our velocity. It's 0, 1, 2, 3, 4, 5. This takes 1 second. This takes 1 second. This takes 1 second. I know. But I just want to make sure everyone's got it. This takes 1 second, right? Okay. This is in meters per second. This is what our meters per second are doing. Okay. Now, how much more am I going? I'm going plus 1 meter per second from what I was doing before. 1 meter per second. 1 meter per second. 1 meter per second more. Okay, see where I'm going with this? 1 meter per second more. Exactly. Exactly. So this is the level of my velocity here. Okay. Now this is the level of my acceleration. So I get this by finding the change in this versus time, right? So this is found as delta v change in v over delta t change in time. Okay. This is what we have going on here. All right. So now let's graph some stuff. Okay. Let's graph it up. So the first thing we'll graph is what is going on our position time graph. So our position time graph will be doing this. Okay. Position in meters versus time. The distance covered in each second is increasing, right? These are evenly spaced. These are not. These are getting greater as I go up, right? I'm covering more and more and more and more as I go. I have a constantly increasing slope. So the tangent lines that I would draw here to indicate instantaneous velocity are constantly getting higher and higher and higher and higher. So these represent, again, velocities, right? Each one of these slopes is the velocity at that given amount of time. Okay, and there's a whole bunch of different ones because it's constantly increasing. Then we're going to take that, and we're going to translate that onto our velocity time graph. Okay, well, we start at a low velocity, and that velocity always increases, and it increases to the right. So we're going to get something that looks like this. Okay, with our final velocity being, well, 5 or 6 meters per second, depending on how you look at it. Okay, time's going by. As time goes by, velocity gets higher. Boom. Okay, how did we get this from this? We found a whole bunch of delta v's, right? We found all these delta v's and we translated their values down to here. So again, remembering from before, the slope here gives that. Okay. And then we're going to go back up this way. And we're going to say we can also make from this an acceleration time graph. Let's make sure we put our units in. Okay, so now we're going to take the slope of this graph, and we're going to translate it down to here. Well, the slope of this graph, the slope of the velocity graph, is not changing. Okay, so we should have an unchanging acceleration. So it should just look like this. Oh, for goodness sake. It should just look like this, right? Our acceleration is constant, and it's equal to the slope that we have here. And now we're going to go backwards. Okay, now we're going to go backwards. So before, right, we said area under here gives me change in velocity, and then area under here gives me change in position. Okay, so let's look at how we're going to deal with this. So the area under here is this. Okay, let's just draw our formulas here. All right, so V, oh, that's no good. V was delta D over delta T. That's how we got to there. And then this acceleration is delta V over delta T. Okay, now going back up, we need the area under here to get the change in velocity. So delta V is area or acceleration times time. So acceleration times time gives us the area under there, and that tells us what our change in velocity was, right? What our change in velocity was. So in other words, if this is 1 meter per second squared, and I go for 5 seconds, my change in velocity will be 5. And that makes sense. I started at 0, and I ended at 5 meters per second, right? So if I increase my speed 1 meter per second for 5 seconds, I got to be going 5 meters per second at the end of that, okay? But now it gets a little more difficult, right? Because now we want to know, well, what's our change in position when we have a changing velocity? But we know it's just the area underneath here. So the question is going to be then, how do we get the area under this? Well, it's a triangle. Close. We're going to do it slightly different. What we're going to do is this, and I'll explain this after. So first, let's draw a line here. We're going to draw a line right here, halfway in the middle of our velocity. Okay. I'm just going to adjust this slightly. Don't really worry too much about the numbers at this point. Just worry about the shape of this graph. So now what I've done here, okay, what I've done here is I've essentially, if you want, actually, hang on, sorry, I'm not doing this very well. Let me just move this up. I'm going to make a little box here. Okay, so make something that looks like that. There we go. Okay. Okay, so someone said use base times height divided by 2. Okay. What did I do? Sorry. I don't know. Just chillax. Okay. So look at here. I've got a rectangle, right? I've got a rectangle. And essentially I need half of this rectangle. Base times height divided by 2. I need half of this rectangle. So I need this area that's like down here. I need to find, you know, this area or half this rectangle, okay? But check this out. Another way to find half the rectangle is simply to like split the rectangle into 2. Oh, that's like a gigantic fat line. I don't like that. That's too big. It's just too big. There. What if I do this? Oh no. Oh, for goodness sake. Struggle. The struggle is real, people. The struggle is real. There we go. Okay. So there is another way to find half of this triangle, right? I could just like check out the whole bottom here. This is, oh man, this is also half the triangle, or half the rectangle, I should say, right? That's half the rectangle. So watch this. This is how we're going to get that. Here's my initial velocity. Here's my initial velocity right here. And here's my final velocity. I'm going to go exactly in between those. So to get this value, I'm going to go VF plus VI, right? VF plus VI, but I'm going to divide that by 2. So I'm going to get like the average of the 2, right? Like to make sense of that, let's imagine that this is 4 and this is 0. 0 plus 4 divided by 2 is 2. Okay, that makes sense. Halfway between. And then I multiply that by time. Now what that is going to give me is the area under this velocity time graph. And what we've done here is we've just derived a new formula for you to use when you have accelerated motion. Okay? So let's write this down. So for accelerated motion, right, if we want to find the displacement change, delta d, we have to do it differently. We can't just say velocity times time because we have a changing velocity. So what we say is we say Vf plus Vi, we divide it by 2, and then we multiply that by time. So this is the change in displacement. So it's actually like how far I went on this graph right here. It's how far I went on this graph right here while accelerating. And I did that by finding the area under the velocity time graph. Okay, so the area under the velocity time graph, when you have a slope on it, is found using this method right here. So just to clarify, this is what we're saying. Okay, so just to clarify what we did there, in case it's not clear, okay? In case it's not clear, for whatever reason, and sometimes, you know, these things aren't super clear right out of the gate. What we're saying here is, if this represents a velocity time graph, and we've convinced you that the area under a velocity time graph gives us displacement, okay? Well then, finding the area under here can be done this way. Go halfway between the two things. Okay? And what you're finding is you're finding half of this rectangle. So in order to do that, right, you're splitting this bigger rectangle in two, which is exactly what you're doing when you're doing base times height divided by 2, right? So we're just doing it in a slightly different way. And the way you get the height of this line is you simply look at your final velocity, always, and your initial velocity. You add them together because you're finding an average, and you divide them by 2. That'll give you the height of the velocity between the two. And then you simply take that and you multiply it by t. Now what that gives you is the area under the graph when your velocity is changing. Okay? So delta d, change in velocity, is Vf plus Vi over 2 times t. Or the displacement that you get, the change in position during acceleration, is found by this formula. So let's do one example of where you might use this. Because you don't necessarily always start at 0. That's why. So watch. Increases in speed. Let's do this problem and then I can take questions after. Okay. So this is a question where you can use this formula. A car is initially at a velocity of 4 meters per second and it increases to 10 meters per second over a time period of 3 seconds while passing on the highway. What displacement was covered during the acceleration? So let's write what we have. Vi, initial velocity, is 4 meters per second. Vf, final velocity, is 10 meters per second. The time that it takes to pass is 3 seconds. How much distance was covered or displacement was covered? So straight up, use the formula as presented to you. Vf plus Vi divide by 2 times 3 seconds. So 10 plus 4 is 14. Divided by 2 is 7. Times 3 equals 21 meters, I think. 21 meters. Okay, so there's the basics of it. So let's just wrap this up by writing down what formulas you have at your disposal. And, you know, you might have to spend a little bit of time looking over this and thinking about it a little bit, okay? So here's what we know. We know that velocity is found as a change in position over time. It's the rate of change in position versus time, or displacement versus time. Your acceleration is found when you have a changing velocity, and it's the rate of change in velocity, okay? Now, building on this, we've come up with one other way of looking at things. Now, this is true when accelerating. So you only use this when there is an acceleration. True when there is acceleration. Otherwise, you would just use the other form of this, right, which is d equals v times t. If the v is constant, then you just use this. If the v is changing, then you got to use this. You got to use the average of the velocity. Okay? I'm going to pull one more formula out of this, and then we're done with formulas. So I want to look at this. True when accelerating. It's only true when there's acceleration. Okay? This is for accelerated motion only. This is true when there is acceleration. Sorry, my writing is horrible. Hopefully my voice will guide you through. Let's look at this. I'm going to rearrange this formula. I'm going to say that velocity is equal to, a change in velocity is equal to acceleration times my time interval. Okay? But now look at this. Delta V is actually found as Vf minus Vi, right? Delta V is Vf minus Vi. So we can rewrite this as Vf minus Vi equals acceleration times time. Or one more isolation, final velocity equals Vi plus At. Okay, so I just rearrange this formula to solve for that. So, putting all the formulas in one big row. Here we go. Velocity, delta D over delta T. Acceleration, delta V over delta T. Vf, Vi plus At, and delta D, Vf plus Vi over 2 times T. These describe accelerated motion for non-uniform. So in other words, for accelerated motion, you got to deal here. For regular, everyday, standard, constant velocity motion, you use this guy. Okay? And that's it.